How is orbital mechanics used to predict satellite positions? Have you ever wondered how scientists and engineers know exactly where a satellite is at any moment? The answer lies in the fascinating world of orbital mechanics, also known as astrodynamics. This science focuses on the movement of satellites, taking into account the pull of gravity, especially from Earth. To predict a satellite's future position, we first need to understand its current orbit. This is done using 6 specific orbital elements or by looking at a position vector and a velocity vector in a 3-dimensional space. These elements define the orbit's size, shape, and orientation, as well as the satellite's exact location within that orbit. One of the key tools in orbital mechanics is Kepler's laws of planetary motion, along with Newton's law of gravitation. For instance, according to Kepler's second law, a satellite travels faster when it is closer to Earth and slower when it is farther away. This means that the satellite's position changes in a non-uniform way, especially in elliptical orbits. To keep track of this, we calculate the true anomaly, which is the angle that indicates the satellite's position along its orbit over time. In the case of circular orbits, predicting the satellite's position is more straightforward. The satellite moves at a constant speed, allowing us to use mean motion, which is the average angular velocity, along with arguments of latitude to determine where it will be based on how much time has passed. For more complex situations, we can solve Lambert's problem. This method helps us find the orbit when we know two positions and the time it took to travel between them. This is particularly useful when we have tracking data from ground stations. However, satellite orbits are not just influenced by Earth's gravity. Other forces come into play, such as the non-spherical shape of Earth, gravitational effects from the Moon and Sun, atmospheric drag, and solar radiation pressure. These factors can cause gradual changes in the orbit, making accurate predictions a bit more challenging. To tackle this, we use numerical simulations and models that consider these additional effects. Ground-based tracking stations play a vital role in this process. They observe satellites and gather position measurements that feed into algorithms designed for orbit determination. By combining multiple observations over time, we can refine the satellite's orbit, which leads to more precise predictions of its future location. These predictions are essential for various practical applications. They help in scheduling satellite communications, avoiding potential collisions, planning missions, and ensuring that satellites stay on course for tasks like Earth observation or navigation. In essence, orbital mechanics combines physics and mathematics to transform current satellite data into accurate forecasts of their positions. This knowledge is crucial for the effective management and operation of satellites in space.